So yeah, whoa. Yesterday we derived the Sulem Zakharov formulation of the water wave equation. Where the nonlinearity n has this expression it's a quadratic term where G of eta is the so-called Dirichlet to Neumann operator. It is defined as follows. This is equal to the square root of 1 plus gradient eta squared times the normal derivative of phi evaluated on the free surface, where phi is the harmonic extension of psi. That is the unique harmonic function which coincides with psi on the free surface, and we further assume that the derivative of phi converges to 0 when y goes to minus infinity. Today, in the second lecture, I am going to study the Dirichlet to Neumann operator using the multiplier method. And to give one application, one possible application to the study of the water wave system. Okay, so today we are going to assume that the variable x belongs to Rd and that d is an integer larger than 1. Firstly, the definition. And we are going to prove these classical results for any Lipschitz function. The Dirichlet to Neumann operator is well defined, and it is a bounded operator from the Sobolev space h1 half of Rd to h minus 1 half of Rd. The proof is in 2 steps. The proof is in 2 steps. First, we prove that there exists a function phi satisfying these 3 requirements. And second, we will prove that we have the right to take the trace on y equal eta. The definition of phi is based on a Poincaré inequality. It's a variant of the estimate that was proved by Poincaré. Poincaré, okay. We are going to prove this inequality. Consider a real number sigma strictly larger than 1. Then there exists a constant c such that for any function u which is smooth and compactly supported in omega, the integral over omega of y minus eta x, you take the Japanese bracket, what is it? To the power minus 2 sigma u of x and y squared dy dx. This is controlled by c times the integral of du over dy squared x y dy dx. So Poincaré was the first to prove a Poincaré type inequality, and he used for that a beautiful argument which consists in doubling the variable. It's a beautiful proof. We are not going to follow it. We are going to follow the classical proof, which is very prosaic. You just use the formula to represent u in terms of its derivative. Using the fact that u is a function with compact support, it vanishes on the free surface. So you can write that u is equal to minus the integral from y to e of x of the derivative. Then you use Cauchy-Schwarz inequality. You use Cauchy-Schwarz inequality, and you get that the integrand here is bounded by this factor times y minus e of x times square dy, and of course on the right, instead of integrating from y to e of x, you can integrate from minus infinity to e of x. Now the conclusions follows from the fact that for y minus eta dy is a constant independent of x and finite. So you simply integrate this inequality with respect to y and then with respect to x, and you get the Poincaré inequality. This is the classical modern proof. Now, in order to define phi, we just introduce a function space which depends on this weight. We introduce the function j, which is the Japanese bracket of y minus e of x to the power minus 2 sigma. We introduce the norm n of u, which is this norm. Okay, we just introduce norm n of u. You take the L2 norm derivative, the L2 norm of j at u, where j is the weight that was introduced here. Excuse me, it's not minus 2, it is minus sigma. And sigma is a given real number larger than 1. Then you introduce the space h1, 0, just a notation, for the closure of the space of functions which are smooth and compactly supported in omega with respect to the previous norm. Then you have three facts. The scalar product, this quantity, is a scalar product on h1, 0. In addition, this space is a Hilbert space and the norm n is equivalent to the norm induced by the scalar product with double parentheses. Okay? And the proof, of course, is elementary. Once you have this function space, you get, by classical duality, that for any function f, which is in the dual of this Hilbert space, you will be able to find a unique function u such that f of v can be written as u. This is this theorem. We apply this with f of the form we are going to apply this with f, a function which is given by the integral of omega of the gradient of capital psi. This is not psi, this is capital psi dot gradient of v dy dx, where capital psi is any lifting of small psi. What does it mean? It means that capital psi is a function in h1 of omega such that capital psi coincide with psi on the free surface. So recall, we want to prove the existence of an harmonic. We want to prove the existence of an harmonic extension of psi. Here, I claim that there exists a lifting of psi, which is much simpler to prove. We just want to prove that there exists a function defined in omega, which coincides with psi on the surface. This is trivial if psi is in h1. Okay, you essentially just take any function. You will take capital psi of x and y of the form chi of y, psi of x. If psi just belongs to h1 half of Rd, there is one argument to give to guarantee that there exists a lifting which is in h1. Okay, one argument, and this argument is easy in the case where eta will be 0 in the half space. For instance, in the half space, you could define a function psi tilde of x and z negative, which coincides with psi on the free surface, and which is more regular. What do? You take a kind of Poisson kernel. Let's say you consider this function. You take your function psi, you regularize it the way you want, and it gives you a function which is in h1 in x and z of the domain Rd plus 1 minus lower space. This is for the case where eta is equal to 0. When eta is not equal to 0, well, the answer is very simple. you take this function and you map it to your curve domain. You simply define capital psi of x and y equal to psi tilde of x eta of x, y minus eta of x. It's easy to verify. It's a simple change of variable. So this function belongs to H1. And it's inside on y equal to eta with psi tilde on z equals 0, which is, of course, psi. Okay? So, there exists a unique variational solution U in H1 0 of omega to the problem what we have defined is a unique function, okay, which is such that f of v is equal to the scalar product with double parenthesis of uv. It means exactly a variational solution to this PDE. Without the tilde. And now we set phi equal to u plus capital psi. This will be a solution to the PDE Laplace phi equal to 0. And phi on y equal to eta is equal to u on y equal to eta plus capital psi on y equal to eta. By definition, we have taken the closure of the space of functions which are smooth and compactly supported for the H1 norm. By a trace theorem, this is equal to 0. And the trace of this function on y equal to eta is equal to psi by definition. So we do have an extension of the function psi, which is harmonic. Of course, more details should be given. But this is the idea of the function phi that we have defined is such that its gradient belongs to L2. This is a variational solution. So it's not at all obvious that we can define the trace of the gradient on the surface. It will be just the trace of an L2 function. But it's not an arbitrary L2 function. This is an harmonic function. And for an harmonic function, we can give a rigorous meaning to this trace. To see it, this is the purpose of the second step. To see it, we are going to use again a diffeomorphism to flatten our domain. So this is the domain omega. And we want to flatten it. So to do so, we consider the simplest of all of diffeomorphism. We map a point x, z here, to x z plus eta of x. This is our diffeomorphism from the lower space to the domain omega. We simply map a point xz in R d plus 1 minus to omega. It means that we set v of xz equal phi of xz plus eta of x. Lemma. We have to transform this diffeomorphism. It's going to flatten the domain, but it will introduce variable coefficient in the PD, of course. It transforms this Laplacian, partial differential operator with constant coefficient, to an operator with variable coefficient. We have that the following PDE for V. One plus gradient eta square dz squared of v plus the Laplacian of v with respect to x minus 2 minus 2 gradient of eta dot gradient dzv minus Laplacian of eta dzv is equal to 0. Okay, you replace Laplace phi equal to 0 by this elliptic equation for v. The Dirichlet to Neumann operator is formally equal to capital U on z equals 0, where capital U is equal to 1 plus gradient eta square dzv minus gradient of eta dot gradient v. And you can also rewrite this equation in terms of U as follows: dz capital U plus the divergence of gradient v minus gradient of eta dzv is equal to 0. So these are three simple identities Okay, how do you get them? Simply by using the chain rule. What is the gradient of v? This is the gradient of phi of x plus z plus eta of x. This is the gradient of phi plus dy phi gradient of eta. And dzv is equal to dy phi with self-explanatory abuse of notations. So v satisfies this equation. And once you expand this operator, you obtain equation 1. This gives 1. This also gives this 2. And then you get 3 by combining the two previous observations. In addition, so this concludes the proof, which is just a chain rule. In addition, by change of variable, you can rewrite what is the Dirichlet energy, the quantity that Riemann minimized in order to prove the existence of harmonic function with given boundary data. You mean the Dirichlet energy can be written as follows. dx. This is just because you see clearly this change of variable. You take a layer here, it maps to another layer here that you just shift up and down. Of course, you don't change the measure. The Jacobian of the transformation is 1. The Jacobian of the transformation is 1. It is something you can see. Well, now it tells you that we are going to write U under the form dZV minus gradient of eta dot gradient V minus dZV gradient of eta. Okay? This belongs to L2. This belongs to L2. This is in L infinity in X and does not depend on Z. So it is in L infinity in Z as well. So this quantity is an L2 function. Okay? Now, since dZu, we have an equation for dZu. This is equal to the divergence of this term, and we have seen that this term is in L2, and this is divergence in X on insist. So this belongs to L2 in Z, with value in which space? In H minus 1 of Rd. Okay? And we have in L2 in Z, let's use the same formalism, with value in L2 of Rd. Okay, we have a function U in this space, and its derivative with respect to Z belongs to this space. You deduce that U is continuous in Z with value in H minus 1 half of Rd. The historical way to prove this lemma is to recall that Jacques-Williot introduced in theory of interpolation together with Pitt and others, following the work of Zygmunt and Sienkiewicz. he introduced his theory of interpolation precisely for the purpose of studying Sobolev spaces of indexes that are not integer to study the trace theorem. And in fact, this is a result of interpolation due to Lyon's, that if your function is in this space and the derivative is in this space, and you have this result. If you don't want to use interpolation, you can simply use energy method. You just say that proof u satisfy dzu, let's say plus mod du, belongs to L2 in Z with value in H minus 1/2. And of course, this is a PDE, an evolution PDE with respect to the variable Z, seen as a time. And you get, by energy method, the same continuity results. This is the proof by energy estimates or interpolation. And you deduce, in particular, U of 0 is well defined because it is a trace of a continuous function, and it belongs to the right space H minus a half. So the proof is okay. Classical. There is one question that we didn't discuss. This is about the boundary condition at minus infinity. The fact that the derivative converge to 0. And in fact, we can prove the following proposition. For any alpha, for any beta, such that the length of alpha plus beta is strictly positive, we have the following result. When y goes to minus infinity, there is decay. A uniform decay. You take the supremum in x at fixed y, then you let y goes to minus infinity, and you have this decay. So, in particular, implicitly, this statement means that this quantity is well defined, which is clear, because an harmonic function is analytic inside the domain, so there is no difficulty. The proof. Thank you. Thank you. The situation is the following. We have a domain and a function phi harmonic in here. It belongs to some L2 space with a weight, and its derivative are in L2. The function eta is Lipschitz, and hence it is bounded. In particular, you can have an hyperplane somewhere underneath the free surface. A flat hyperplane fully contained in the domain. The function phi is in L2 with a weight. Its derivatives are in L2. You denote this domain here by S, the strip. Phi belongs to H1 of the strip. Okay? And since it is in H1 of the strip, by the easiest of all possible trace theorem, the one when you take the trace on a flat strip, and that you can prove by a direct integration, in fact, phi, you get that you can take the trace of phi on y equal minus h, and this belongs to L2. Not h half, L2. L2 is trivial. Okay, so we have a function here, perfectly well defined, a function here, and it's perfectly well defined, and this is flat. In particular, what you can do, you can perfectly define what is the harmonic extension of this function in this half space, the half space located underneath this hyperplane. So you have one harmonic function, but phi is harmonic. So when you restrict phi to this half space, it's also harmonic. So you have two harmonic functions that coincide on this hyperplane. They are equal. So phi is equal to the harmonic extension of this function, which is an L2 function. And for an L2 function, this is trivial to prove. This is Plancherel and the Poisson kernel. So this decay can be proved just by this trick, saying that, well, phi is equal to the harmonic extension of its trace on any hyperplane located in the domain. And then, since you have invariance by spatial translation, you can apply Fourier analysis, and you are done. Talking about trace theorem, there is this result. That we prove with my colleague. Excuse me. That we prove with my colleague Cauchy from the Chinese University of the Chinese Academy of Science. That says that consider a function u in the space considered before. The function u in L2 of the weight space whose derivative belongs to L2. Here, again, omega is a curved half space located under the graph of the function eta, and eta is Lipschitz. Then, set f, which is equal to u restricted to y2 equal to eta, which is a function in h 1/2 of Rd. Set. Then you have this inequality. The L2 norm of the derivative of u are bounded from below by the integral over Rd of f g of eta f dx, which is in turn bounded from below by some constant c times f in h 1/2 dot square divided by 1 plus gradient of eta in BMO. Okay? So, this is an inequality that controls the trace in terms of the H1 norm of the function. This is the classical trace. It contains the classical trace inequality. Why is that? Because the BMO space, or the BMO semi-norm, is defined as the supremum over all cube. You take the integral over the cube of f minus its average over the cube. you measure the oscillation and you say that it is a space of bounded mean oscillation. Okay, either you do know this space or not. If you don't know this space, there is one clear embedding. It's a larger space that contains L infinity. In particular, you can replace BMO by L infinity here. And then you get an improvement of the usual trace inequality. Another embedding that you might like is this one. This one, and there's also this one, and there is also, if you like, a triple space. There is sometimes people say BMO is this space. Yes? The weight is G. Thank you. That's good. Concerning this statement, this is the first remark that I want to make, that it improves about the regularity because it is BMO instead of L infinity. The second improvement compared to the classical trace inequality is that the dependence on, let's say, here there is a factor, and the dependence in this factor is optimal. You cannot have the same inequality with a weight that will be better than this one. For example, it would be false to say that this inequality holds. You necessarily have to divide by 1 plus gradient eta to add. How do you see this? Well, there is a remark. Introduce theta. This is a fun function considered by Riemann. This is the harmonic extension of eta itself in the domain defined by eta. You introduce the harmonic extension of eta. Then claim let's assume the domain is periodic to simplify. This quantity, the Dirichlet energy associated to theta, is bounded by, let's say, 2 times eta in L infinity times the measure of the torque. We assume that the functions are periodic. There is no typographical error. There could be one because this is a quadratic term and this is linear. Quadratic, linear. Huh? It's not so obvious that it holds. But the proof is straightforward. This is the Dirichlet energy. The harmonic function is the one that minimizes the Dirichlet energy. So you just have to find a function that is close to minimizing. Let's say you take a function of the form chi of y, y. Excuse me, you start with a function y. Y will be a function that satisfies y evaluated on y equal eta is equal to eta. So it satisfies this, okay? but it is not in the space of functions that are decaying to 0 as y goes to minus infinity. So you have to put a cutoff function. You have to truncate. But how do you truncate? You have a domain. And you will need to truncate below the lowest possible value. And the lowest possible value is determined by the L infinity norm. Okay? So it's enough to truncate there. And by so doing, you get a function with a cutoff function that coincides with it on the surface. That is a possible competitor. You compute this energy. You look at the derivative of this function. This is essentially 1 integrated from the lowest possible value to the top. It has to do with the L infinity norm of eta. And this is how you get this inequality. So you have this bound from above for theta. And you have this possible lower bound from below. And you try to improve the exponent alpha. And then you apply this with a special choice for eta. You are going to choose cosine of kx. Here you have cosine of kx in h1 alpha squared. This gives you square root of k squared. Below you will have something like k to some power. And on the left you have the L infinity norm that does not depend on k. You have 1. Necessarily, alpha has to be larger than 1. So this estimate is optimal in this meaning. And eventually, a last comment is that I think that the proof of this trace inequality is in a sense simpler than the classical one. I am going to give it. Proof. Firstly, this has already been proved. Okay? There is something classical. This is the fact that this is larger than the gradient, the L2 norm of the derivative of phi, where phi is the harmonic extension of f. This is how you get a variational solution by minimizing the Dirichlet energy. And we have seen yesterday, by using Stokes' theorem, that this is equal to this. So the inequality on the left is classical. We have to prove this inequality. We use the change of variables that we consider already in the previous proof. I mean the trivial change of variables that flattens the domain. I assume, to simplify notation, that x belongs to R, that is, that the space dimension is 1. Then I set Q, the quantity, this quantity, and we have seen previously that this is equal to the square of the ZV plus
set V. Why is the same thing for V and phi?
Ah. Thank you. Thank you. This is V of x and z. This is written here. Okay. This is on one end. On the other end, what do we have? we have that this norm, the h1/2 norm of f, is by definition this, and by Plancherel this is equal to this. This is by Plancherel. By Plancherel. So we are integrating on R, and now I just say that this is equal to this. Why is that? Because f is equal to v on z equal to 0. Okay? F is equal to v on z equal to 0. Mod df is equal to mod dv on z equal to 0, because there is a tangential operator that commute with the operation of taking a trace. Then this is Leibniz. I have two terms. I apply Leibniz, I get two terms, but in fact, these two terms are equal, because you can apply Plancherel and move mod d from this factor to this one if you think that you are integrating in x first. Okay? Because mod d is self-adjoint. This is because mod d is self-adjoint. This is a Plancherel again, a Fourier multiplier whose symbol is real. Now, we want to avoid using mod d. We want to use the usual derivative, and for that, it's enough to introduce the Hilbert transform. What is h? H is the Hilbert transform. It acts on a function, let's say, in Fourier, by multiplying the Fourier transform by the sine times minus I. Now, we further transform this expression, and we make appear the derivative that we do control. We are not controlling dxv. We just know that this vector field acting on v gives an L2 function, not dx. So we make appear this vector field by subtracting and adding we just subtract and add eta x vz. Okay, so here we have a term 1, and here we have a term 2. 1 is obviously smaller than q. Not obviously. 1 is smaller than q. Q is this quantity, this quadratic quantity. This is a bilinear quantity. we apply Cauchy-Schwarz. We are going to say this is smaller than, we have a coefficient 2, this is smaller than dZv squared plus this block squared. In this block, we have the Hilbert transform. But it's obvious that the Hilbert transform, if it is defined in this way, it's clear that it is an operator bounded from L2 of R to L2 of R, and whose operator norm is bounded by 1, simply because its symbol, modulus, is bounded by 1. This is for the analysis of term 1. The analysis of the term 2 requires one more trick. So we notice that the term 2 is equal to, there is a coefficient 2. We have two terms. We write them separately, in a sense. Okay? The first term, we do not touch it. And the second term, we move the Hilbert transform from this term to this one, using the fact that the Hilbert transform is skew symmetric. Why is that? Because the symbol is purely imaginary. So we move, and when we move from this term to this one, we change the sign. So we get this term minus this one, and now you observe that you get a commutator structure. So this term is equal to the integral of dZv times the function that you get when you commute the Hilbert transform with the multiplication by the function eta x dZv. This term is in L2, this term is in L2. And you recall a classical estimate from harmonic analysis that the commutator of the Hilbert transform and a function, let's say g, is bounded from L2 to L2, assuming only that g is in BMO. If g is in L infinity, the Hilbert transform is bounded on L2, the multiplication by g is bounded on L2. It's obvious that the commutator is bounded on L2, because every term separately is. Once you know that this is a commutator, you can exploit one cancellation to say you don't need g to be in L infinity. BMO is enough. So this is the proof of the trace inequality in this case. Okay, so far we have discussed inequalities that have to do with the fact that the Dirichlet to Neumann operator is an operator bounded from h1 half to h minus half. And this is a problem that you encounter in many problems in partial differential equations. People working in harmonic analysis, for some reasons that I think are historical, were interested in potential theory. Potential theory, you don't want to study the harmonic extension of a function like before, psi, which is in h1 half, which is a natural thing to do if you are from PDE. People want to consider harmonic extension of functions which are in LP, probably because it is more difficult. I have discussed with many people. Okay. And the only explanation about the physical motivation was, well, in fact, you have to assume that the normal is in BMO. And it's more complicated. But, anyway, if you do that, a trace in LP, a normal vector n in BMO, the problem becomes so difficult that you have to use some identities, some tricks. And this is how, in the 80s, Jerison and Koenig develop a beautiful theory to study this problem. And they rediscover an identity very old and known in the field of scattering theory by people doing applied partial differential equation as relic inequalities. Relic inequalities have to do with the fact that the Dirichlet to Neumann operator, G of eta, maps H1 to L2. And that the operator norm is bounded by the Lipschitz norm of eta. Okay, this is a relic inequality. And I want to show you a very simple proof of the relic inequality. I want to prove the following proposition that we prove with Sidant Agrawal. We proved several inequalities. I am going to prove this one. Assume that we have a domain which is C1. C1, eta is bounded, its derivatives are bounded. Consider a function psi in H1 of Rd. Then, look, in any dimension, then there is this inequality, g of eta psi squared divided by 1 plus gradient eta squared dx is smaller than 4 times the integral over Rd of the gradient of psi squared dx. So, clearly, obviously, this implies the relic estimate. Because if you know, if you have a bound for a gradient of eta in L infinity, okay, and you also have an explicit value of this constant. Bon. That's one point. And the second remark is that you see the constant 4 does not depend on the dimension. The proof so relic is inequality, and the proof by relic of this inequality plays a fundamental role in analysis in various places, because it's probably one of the people use the multiplier x dot gradient. Okay? The multiplier x dot gradient. This is very classical because it was popularized later by Moravec in his pioneer work on scattering, by Jacques Williams to prove observability, by Pozaf and Dirichlet to study elliptic PDEs. Relic was also studying an elliptic PDE. He considered this multiplier x dot gradient. Why is that? Because he was considering the eigenfunction of the Laplacian in a domain which is star-shaped. And he wanted a vector field which is transverse to the boundary. For our problem, the natural vector field transverse to the boundary is this one. Okay? The vector field dy. So we multiply the equation Laplace phi equal to 0 by dy phi. And we integrate. What do we get? We get that 0 is equal to the integral over omega of the Laplacian of phi dy phi. And we are going to integrate this. So this is dy squared plus the Laplacian in x. So we have clearly dy of 1/2 of dy phi squared. We have also plus divergence in x of okay. So this is just Leibniz formula. We have this. Now, there are two terms that integrate trivially because it's an exact derivative that you are integrated from -infinity to the top. It gives you the integral over Rd of 1/2 of dy phi squared minus 1/2 of gradient phi squared evaluated on y equal to eta. And then it remains to this term. You apply Stokes. What you get is minus gradient in x of eta times this quantity. So we have only quantities evaluated on the free surface. And now the classical proof of Relic inequality consists in applying Cauchy-Schwarz inequality at that point. We are just going to perform one more computation before applying Cauchy-Schwarz inequality. Remember that we have introduced these quantities. In terms of these quantities, what we have proved is, in fact, this result this is what we get. Remark, it means exactly that that the integral of the nonlinear term in the Zakharov system is equal to 0. So it's a way to understand something about the nonlinearity. Okay. Of course, if gradient of eta is in L infinity, by applying Cauchy-Schwarz inequality, you can derive from this identity the fact that B and V are equivalent. But we are going to perform one more identity. We replace V by its value in terms of psi and B. You replace here and here V. We have checked this computation yesterday. What do you get? You get exactly this. The L2 norm of B, and in fact 1 plus gradient theta squared, the L2 norm of B, is equal. There is no inequality in here. Is equal to the gradient psi squared. Okay? This is equal. And then, how do we conclude the proof? We just write that g of eta psi this term, the integrand that we want to estimate, is smaller than, and this is Cauchy-Schwarz or Jung. Okay, this is trivial. But this coincides with 1 plus gradient of eta squared b squared. So we know that when you integrate, this is equal to this term. When you integrate this by Cauchy-Schwarz, this is smaller than the gradient of psi. So you get directly the constant 4 here, independently of the dimension. Now, about the possible application of this to the water wave equation. Okay, so we have seen several inequalities. How can we apply them to study the water wave equation? Yesterday, I have said that Rayleigh proves that the kinetic energy is different from the potential energy for Stokes waves. Okay? So this contradicts, in a sense, a principle in physics that says that, in average, the kinetic energy is equal to the potential energy, because the wave propagates because of an exchange, a perpetual exchange of energy between kinetic and perpetual, like a pendulum. Okay, you have a pendulum. When it is on top, you have only potential energy. At the bottom, it has only kinetic energy. It's an exchange. So you do not have equidistribution of energy. However, we are going to see that there is, for water wave, a version of equipartition of energy in the form of a virial theorem. So this is something I was happy to understand. Because I was always wondering what virial means, because I have seen virial in many talks in PDF. And the name of virial comes from a theorem proved by Clausius in 1870. He proves the following. He has a paper where it's about thermodynamics. And there is one statement, theorem, and the statement is the following. The mean vis viva of a system is equal to its virial. So it explains what is a virial. This is the mean vis viva. If you want to understand this, you have to go back to that century. Vis viva is a beautiful expression. It goes back to Leibniz to say kinetic energy. It means living force, and in French it is still used when you say les forces vives ou l'énergie vive. It is still used in the language. So this means kinetic energy. It's a less prosaic way to say kinetic energy. So what is virial means? Well, virial is the conclusion of the theorem. This is a name invented by Clausius. That's it. So this is the explanation, because there are many people talking about virial. They say virial. Virial does not exist. Virial. This is a Latin word. A Latin word that does not exist. So to explain the theorem, let's look at the proof. So Clausius considers an Hamiltonian equation. d over dt of q is equal to p d over dt of p is equal to minus v prime of q, where v is a function. And let's simplify. Let's consider a simple function. When Clausius says the mean is viva of a system, he refers to a Hamiltonian system. Now, introduce an action, that is a function. This function, 1/2 of p times q. And compute. You compute what? You compute the evolution of this action. You apply Leibniz. Let's say you differentiate q. What do you get? You get p. So you have 1/2 of p of t squared. If you differentiate p, you get minus q times v prime of q of t. This is one computation. Another observation that has to do with the fact that the system is Hamiltonian is that I is bounded. This is Cauchy-Schwarz plus the fact that the energy is conserved. I is bounded. So you can write that 1 upon t, integral from 0 to t, of 1/2 of p of t squared minus q of t v prime of q of t dt. This quantity is equal to, well, what you get when you multiply, you integrate this and you divide by capital T, you get I of t minus I of 0 upon capital T, which is bounded by capital C divided by capital T, where C is a constant. This is because capital I is bounded. So, in particular, it goes to 0 when t goes to plus infinity. And this is what Clausius means by the mean. The mean means the average. And when he says is equal, he refers to the fact that asymptotically it is equal to. And this is extremely well explained in his paper. Clausius already considered in his paper, and this is nice, that solution could be either independent of time in a sense, or time periodic, or, and here's a word that I have forgotten to say, general. And this is exactly what we are doing in PD when we consider traveling wave, periodic in time solution, or the Cauchy problem. He already had the three motivations in his mind. So, to conclude, this is 1 of p squared is the kinetic energy. This is a vis viva. Well, and this is, by definition, the virial. This is it. So, with Claude Zully, from the Université Paris-Saclay, we prove the existence of a virial identity for water wave. One fun fact, For the water wave, the Hamiltonian is quadratic. I say, at least at the level of symbol, it is quadratic. But we still have a virion. And we are going to prove that in average, this is the potential energy, which is equal to a modified version of the kinetic energy. For Clausius, this is the kinetic energy, which is equal on average to a modified version of the potential. We are going to prove for water waves that this is the potential energy, which is equal to a modified version of the average. And our virial identity is the following one. We consider this action, okay? You see there is a kind of duality. This is a duality product, which on R turned out to be the real product. This is a duality product. For the Hamiltonian water wave equation, the duality product for Zakharov formalism is just the integral of eta times psi is equal to, well, the integral of omega of 1/4 of dx phi squared plus 3/4 of dy phi squared dy dx minus g over 2 the integral of eta squared dx. Okay? Corollary for Stokes wave, potential energy is equal to this modified version of the kinetic energy. The kinetic energy is this one with 1/2 and 1/2. Here you have 1/4 and 3/4. The second corollary, this afternoon, if I am able to do it, I want to discuss the Cauchy problem. The well-posedness of the Cauchy problem, and to say something about the tools used in the proof. This is for the stable case. Eric, please. Okay. In the unstable case where the gravity is negative, and it happens when you reverse. The heavier fluid is on top of the lighter one. It is, for example, considered by Kuhl in his reference survey paper. What do you have? There is the following result. Let's consider any eta 0 initial data. Assume that initially the fluid is at rest. Then you have this inequality. For any initial data eta 0, you start with the fluid at rest. No fluid velocity to simplify the notations. Then this quantity will grow in time. Whatever is your initial data, you have a very small bubble. This quantity will grow. What does it mean? In particular, it means that it justifies, in a sense, the formation bubble for Rayleigh-Taylor instability. This is the first step of the formation of the Rayleigh-Taylor instability, is that you have a steepening of a front square And after that, it happens something very complicated, the mixing and a lot of bubble that we don't understand. We just say that for any initial data, there will be a steepening, that is the formation of a large slope. First remark, and also remark, from a mathematical point of view, it's perfectly legitimate to assume that G is negative because it is in the reference paper by Cauchy. This is a good equation. And also solutions do exist in this setting. It suffices to consider analytic initial data for which you have a kind of Cauchy-Kovalevskaya theorem because it's a system of order less than 1. So we do have solution in this case, provided that the initial data are analytic. And that concludes what I want to say using this method. Thank you.